You sent a message on WhatsApp today without thinking about it. Back in 2014, the machine behind that little tab was moving 40 billion messages a day, 2 million live connections on a single server, around 32 engineers running all of it. A team that small should not have been able to move that much. So, how does so little run so much? Follow one message. From the moment your thumb hits send, your phone isn't making a fresh request for every text. It holds one persistent TCP connection, a single long-lived socket, opened once and kept open for hours. No reconnecting for every message, but a warm pipe has a price. Every open socket is memory and a file handle the server has to hold, even when nothing is being said. Multiply that by hundreds of millions of mostly idle phones, and just keeping the connection alive becomes the hard part. Before the message even leaves, it gets squeezed down into a compact binary protocol called FunXMPP, swapping verbose tags for single byte tokens to save bandwidth and battery. The slimmed down message travels up that socket and lands inside a process that exists only for you. This is the heart of the design. It's called the actor model. The backend was built almost entirely in Erlang, a language that came out of the telecom world. Every connection becomes its own lightweight process on the Beam virtual machine. Not a thread, not a request handler, just one tiny isolated worker per phone, alive for as long as your circuit stays open. That isolation is everything. When one process crashes, it dies on its own, and a supervisor responds a clean one instead of taking the whole box down with it. Erlang engineers call this let it crash. None of it comes free though. Erlang is a niche language with a high input to match, and it was never built for raw number crunching speed. What it was built for is holding millions of things at once without falling over. That was the trade they made. Now, the message needs a destination. Your process asks one question: where does the recipient live right now? The answer sits in Mnesia, Erlang's in-memory distributed database. It holds the routing table that maps every user to their server, around 2 terabytes of it, all kept in RAM. An in-memory lookup is fast enough to run on every single message, which is exactly what routing tens of billions of them demands. But RAM is expensive, and an in-memory store has to be replicated carefully, so they traded durability and cost for speed. And one message isn't always headed to just one person. Send it to a group, and your phone still uploads it exactly once. A single copy tagged with a group ID. The expansion happens on the server. It looks up every member and queues a separate copy for each one. This is server-side fan-out, and it is why the numbers never quite add up. On the 2nd of April 2014, 20 billion messages people sent fanned out into 44 billion delivered. 64 billion in a single day. That gap is fan out made visible, and the cost scales with the size of the group, not how many people are typing. Either way, the message still has to reach a person. If they are online, your process hands it straight to theirs, and it flows right down their open socket. The servers never let two phones talk directly. Everything routes through the middle, in a pattern called store and forward. But the recipient isn't always there. Phones die, Tunnels swallow the signal. People fall asleep. If no one's there to receive it, the message drops into an encrypted offline queue and waits for up to 30 days. Come back inside that window and it drains. Come back after and it's gone. The server is a relay, not a mailbox. And those little ticks you watch are that relay reporting back. One grey tick means the server has it. Two grey tick means it reached the device. Two blue tick means it has been read. The ticks are the architecture leaking through onto your screen. Up to now, the server has known everything. Where you live, when you reconnect, which queue is holding your backlog. Encryption is where that knowing stops. In November 2014, WhatsApp partnered with Open Whisper Systems, the people behind the Signal protocol. And by April 2016, end-to-end encryption was on by default for over 1 billion users. A pre-key handshake called X3VH lets two people agree on a shared key, even when one of them is offline. Then, the double ratchet takes over, deriving a fresh key for every single message. So stealing one key never unlocks the rest. Now, the routing, the queue, and the fan out all move ciphertext the server can't read. It knows where to send the envelope. It just never learns what's inside. But that blindness has a bill. A server that can't read your messages can't search them, can't scan them for spam, and can't rebuild your history on a new device. That sealed envelope assumed one key person. And these days, people live on more than one device. So in 2021, Meta solved it with something called client-side fan-out. Every device gets its own identity key, and the sender encrypts each message separately, once for every device you own. The server still holds no key, just a directory of where those keys live. And when you link a new laptop, your history doesn't come from the server. Your phone encrypts a slice of your recent chat and hands it over directly to your laptop. And all of this run on metal you can point to, not Linux, but FreeBSD. Chosen for its mature TCP stack and a kernel you could tune deep. They bought big bare metal boxes and tuned them hard, instead of spraying out lots of small nodes or instead of doing horizontal scaling. And they didn't just rent the hardware, they patched the Beam runtime and the FreeBSD kernel themselves, hunting down lock contention. That bought them control, but it cost them elasticity. There is no auto-scaling, so you carry the capacity and the failures yourself. And there's one last trick. Erlang can load new code into a running system, so fixes ship without a restart, and the processes never stop. That's the near zero downtime claim. But resilient is not the same as invisible. On the 22nd of February 2014, just 3 days after the $19 billion Facebook deal, WhatsApp went dark for about 3.5 hours. The architecture absorbs failures, it doesn't abolish it. So that's one message, socket, process, lookup, handoff, queue, text, envelope. Now multiply it. A single chat server doesn't hold one connection, it holds millions. Back in 2011, one box already held around 1 million. By 2012, an engineer named Rick Reed pushed one past 2 billion at an Erlang factory talk. In production, they ran each near 1 million on purpose, leaving headroom for failure and spikes. And the volume climbed right alongside it. 10 billion a day in 2012, 40 billion out by 2014, roughly 100 billion by 2020. And the fleet that hauled the 2014 numbers was small, around 550 servers, over 11,000 CPU cores, 147 million phones connected at once, at peak. Which leaves the one question hanging over all of it. Who was actually running this? WhatsApp was founded in 2009 on a deliberately lean, do-less culture. No ads, no games, no gimmicks. The architecture is that culture written in code. Roughly 40 million users for every engineer on the team. The per-user process. The supervisor that restarts what breaks. The in-RAM lookup, the blind pipe, every one of those was a choice that let a tiny team sleep at night. The leverage wasn't an accident, it was the whole point, and it wasn't free either. A team that small is a buzz factor waiting to happen. The leverage and the limits were the same decision. 40 billion messages a day, run by a team of roughly 32. That message you sent earlier without thinking, it made this exact trip. One socket, one process, one envelope, the server queries but can never open. One more thing before you go. If taking a system apart like this is your idea of a good time, please subscribe. That's the whole channel. And I'm genuinely curious, which of WhatsApp trays would you have made differently? Tell me in the comments.